Okay, so this is the third problem in the IB, higher level applications and interpretations, Oxford textbook problem. And it's basically having you guess whether these following conjectures are true or false. If it's true, you need to go and justify it with a proof. And if it's false, you need to go and provide a counterexample. Now, I have some scratch work written already here because I am terrible at coming up with counterexamples on the fly. So first we have here a times b, square matrix raised to size dimension n. Does it equal a to the n times b to the n? And then given a scalar k, it could be a real number. Heck, it could even be a complex number. This k times a raised to the power of n equal k to the n times a to the n. And here's what my intuition says. The first one is false due to matrix multiplication not being commutative. But the second one is true, and given that n is a counting number, we'll have to prove this using induction. So the counterexample for this, which will be the hardest thing for me, because, dear goodness, I haven't been in practice for these types of problems in a while. Let's try the counterexample with n equals 2, so we're just dealing with 2 by 2 matrices only, and let a and b be these following 2 by 2 matrices here, where a essentially represents the vector of vertical arrows, one going up, the other going down, and B as a matrix represents the set of horizontal arrows, one going to the left and the other going to the right. And yes, the order that you slot them in your matrix does matter. So quantity AB squared equals AB times AB equals these things here. And then because I'm boring, I'm going to secretly do my matrix multiplication from left to right. Although you could multiply any two matrices which are next to each other, because matrix multiplication is associative. So let us go and gun through the horror here of stuff. Okay, this is going to be 0 times 1. Oh, sorry, 0 times 1 plus 0 times 0. This is going to be 0 times negative 1 plus 0 times 0. This is going to be 1 times 1 plus negative 1 times 0. This is going to be 1 times negative 1 plus negative 1 minus 1, negative 1 times 0 here. And then the other two remaining two matrices here are the same. Let's go and paste this here. Let's go and expand this out. So that just seems to be 1. I'll have 3 matrices now. Just a digressive forewarning, when you get used to it, I really do not recommend doing any matrix algebra or linear algebra in Microsoft Word Processor. It is just atrocious because it can only handle 2 by 2 or 3 by 3, and you can't type it out. If I say that, there's LaTeX here, but ultimately I think it's like better to go and like do it on Overleaf. Again, problem with me is I am horrible at coding, so yeah, that's just what it is. 0, 0. Let's see, negative 1, 0. Yeah, this is 1 here. This is 1. So I got negative 1 again from here. Okay, interesting. Oh, wait. The 0, 1, 1, negative 1, 0. Okay. Zero, 1, 0, negative 1. So if I take this and I multiply it by these things flipped over, I basically get the same result for this. So somehow this ends up being sort of like an identity matrix multiplication of a sort. But then I can go and like multiply these two matrices together. This will give us like 2 matrices in total. Let's see. 0 times 0 plus 0 times 1. And this is 0 times 0 plus 0 times negative 1. This matches up here with this over here. Now I'm going to do 1 times 0, 1 times 0 plus negative 1 times 1. And this is 1 times 0 plus negative 1 times negative 1. And then we copy and have the same matrix over here. One, 0, negative 1, 0. Let's see what we get. This is 1. This is 0. This is negative 1. Okay, good, we're getting something different this time. And then this is 1. Okay. And then multiply by this result. I'm sorry, I hate computations. That's just me. Okay, and then the last one, you get 4 results here. So then this is 1 times 1 plus 0 times 0. 1 times negative 1 plus 1 times 0. And then this is negative 1 times 1 plus 1 times 0. This is negative 1 times negative 1 plus 1 times 0. And these arithmetic mistakes are going to be the killer of me. This is 1, negative 1, negative 1. Negative 1 times negative 1 becomes positive 1. Okay, good. So that's what we get here. Now we multiply these two things together and see what we get. Actually, just so that we don't reinvent the wheel, did we multiply any similar things together a while ago here? Ah, yes, we did. If we get this and like multiply by that thing, we basically get the same result here. Let's see. Oh, yay, goody. I could save some time. Okay. Because, yeah, we good mathematicians, even more so than physicists, like to be lazy or stuff. Or especially me when it comes to computation. So we already multiplied this a while ago, which was this expression down here in the middle. So you can get this thing here. Whoops, sorry. Give me a second. Let me copy this, paste this here. This basically ended up becoming, where was it? 0, 1, 0, negative 1 over here. I'm reading it for the columns, not the rows, sorry. Let's see. Yeah, that's what I got. So then we get one copy of this, and then one copy of that. But then recursively, we can do like the same result again. This is basically identical multiplying this by this again, a second time. So this simply gives us this again. And then we multiply these two matrices together. Now, let's see. Please tell me that I multiplied those two before. Yes, I did. And I got... Okay, 1, negative 1, 0, 1. Is that what I got? Yeah, that's what I got. Okay. So then this becomes... Okay. 1, 0. No. No. God dang, what was it? Oh, sorry. 1, negative 1, 0, 1. So it's basically almost this thing, except like the top right corner, this entry is 0 instead of negative 1. Okay, and finally, we can put them together. When comparing them together, where is it? Yeah. AB squared. These two matrices clearly do not equal each other component-wise. So then we can say, yes, this does not hold true in general. And one counterexample, this is a key thing when doing like falsifying stuff with a counterexample. One counterexample suffices. You don't need to go and generate a whole bunch of other things. Yeah, these are not equal to each other. This counterexample disproves the first conjecture. Okay, now the stuff that I'm more comfortable with, proving the second conjecture, which is completely fine because scalar multiplication is both associative and commutative. And this we can prove since n is a counting number. We prove this by induction, so let's see here. Let's take this, copy the statement over here. Oh yeah, and really when you're like multiplying each individual vectors by itself in matrix multiplication a la function composition, it's really gonna do three things. It's either gonna like translate the vector, rotate the vector, or stretch or shrink, dilate out or in the vector. So if you want, you could play around with like GeoGebra, Desmos, or heck even Manim, and see geometrically from a computer graphics perspective what that would look like. Because then again, I'm not good at coding. But anyhow, back to here. This comes out. This proves the first conjecture here. Let's go to here. Okay, so proof by induction. What are the main steps? You gotta prove the base case. Assume inductive hypothesis. Take the inductive step. And then use inductive hypothesis and base case, if necessary, along with any other algebra, with any other relevant mathematics. To solve the problem. Okay, so first off, let n equals 1, since n is in the natural numbers. So the left-hand side expression becomes Ka. Right-hand side expression, on the other hand, is k to the 1 times a to the... God damn it. A to the 1. And this is also Ka as well. So then each of these sides are equivalent to each other. We're good here. These two expressions equaling each other. Now we assume the inductive step. Assume that Ka to the n equals k to the n, a to the n. This is our inductive hypothesis. Now inductive step time. So Ka to the n plus 1. Now using exponent rules, essentially, you have like n multiples of the matrix Ka being multiplied with an additional 1 matrix Ka. So this can be split up into Ka to the n times Ka. But now by the inductive hypothesis, this substitution follows. Yeah, which is basically this thing over here. This next substitution follows here, which is then k to the n, a to the n equal, times ka. And we can commute scalars around. So this leaves us with k to the n k. I could have moved this k to the left or to the right of k to the n, it doesn't matter. But this leaves us essentially with a to the n times a next to each other here. I didn't move the matrices around, I only moved the scalars around. So now I can just combine this using laws of exponents. So yeah, the algebra really, in essence, is laws of exponents. Get k to the n plus 1, a to the n plus 1. And done. And so this is one of the caveats I mentioned why I do not like how linear algebra is structured for the applications interpretations at first glance, although I'm glad you do stuff like eigenvalues and eigenvector stuff, is because to prove the foundations of the steps, you need proof by induction. And proof by induction, the curriculum is only taught in the analysis and approaches course. So if you're an applications and interpretations audience looking at this video, you might be completely flabbergasted at what I'm doing here. But yeah, the relevant math I'm using is exponent rules. And that's basically it. We're done. So then this statement, you prove P of 1 is true, and assuming P of n is true, we proved P of n plus 1 is true. So the conjecture k a to the n equals k to the n a to the n holds true for all natural numbers n. And we are done.